Hey guys, this is Mrs. Harbin and this is Algebra 2, Section 2.4, Modeling Linear Data. Now, modeling just means to show something, usually something pictorial or three-dimensional. So we're going to take some information that we can graph linear in a straight line, and we're going to model that or show that on a graph. That's all we're doing. Just a reminder, our biblical correlation for this chapter is Hebrews 3:12-14. It says, "See to it, brothers, that none of you has a sinful, unbelieving heart that turns away from the living God, but encourage one another daily. We have come to share in the Christ, if we hold firmly to the end of the confidence we had at first." We pray for you guys daily as students that you will form good relationships with others, relationships that will build you up and will lead you in a positive direction. We know that relationships exist all throughout the world in all various fields, math, science, English, history, and that relationships can either be positive or negative. We're going to see that also in math when we're looking at the relationships between x and y, which is a function of x. And we're going to see this relationship exists between two various points. And let it be a reminder to you that you are in a relationship with people, with your family, with God, and that all of those relationships can affect the decisions that you make. Our lesson objective for today is this: you, the student, will create scatterplots and linear models, plus evaluate linear models. Data with two related variables are called bivariate data. Bi means two, variate means variable, so two variable data, bivariate data. That should make sense to you. A scatterplot is used to show the relationship between two such sets of data. So let's take a look at some real-world data here. We have training miles listed here on the left, and that's going to be our x variable down on this x-axis. And our 10K runtime to the nearest minute is our y data, or y-axis data. And we've graphed those different points along here on our graph here. So we have 170, we have 267, we have 353, 455, 544, and 647. So it looks like the more miles that you train with, the faster your time gets in that 10K. So this is an example of data with two related variables called bivariate data. Again, we have two variables. Our first variable is the training miles, and the second variable, or the second thing that changes here, is your 10K runtime. A trend line can be drawn to model the relationship between the two variables. If we go back to our graph, you'll see that it's not strictly linear. If we connected all these, it wouldn't be a straight line. It would be a little bit of a jagged line. But we can put the line of best fit, or a trend line, between these points, trying to minimize the distance between the data points. It can be used to make predictions or to predict trends. So first, plot the points from the given data, which we've already done. Then estimate and draw a trend line. Now we don't want it up here above the data. That would be too far away. And down here is not best either. So we can put a straight edge down, and what I like to do is try to connect the first and last point using my straight edge and kind of draw my line right between those 2 points. And it will pass between the other points. Right? Once we have our trend line, we can then determine the equation of that trend line and write a linear equation for this data. First, choose 2 points that are on the line. In this case, we're going to choose 2 points that intersect right here, the green points. That represents 280 and 60, and this point represents 480 and 50. Okay, once we have our 2 points, we can find the slope using y1 minus y2 over x1 minus x2. We find our slope is -1 over 20. Because this is a real-world problem and we are dealing with minutes, we are going to convert that to decimals, since minutes are not usually measured in fractions. If you think about your stopwatch, you're not measuring in fractions, you're measuring in decimals. Then we'll use an equation to find the y-intercept. Our equation is y equals mx plus b. We already know our y from one of our points is 60 and our x is 280. We know our slope is -1 over 20, or -0.05. And we will then solve for b and find out that b equals 74. We're going to plug those variables for m and b only back into our equation to get the equation for the line. We get y equals negative 0.05x plus 74. And that can be used to help us predict how fast our 5K time would be at various mileages. So if I only train 10 miles, for example, before my 10K, that can help me predict how fast, or rather how slow, my time would be in the 10K. So let's predict the number of training miles needed or required to complete the race in 30 minutes. So here's our equation. And if you remember, minutes was our y-axis. So we're going to plug 30 into the y and solve for x. And we see that in order to run a 5K or 10K in 30 minutes, we need to have at least 880 miles of training, according to our data in the prediction. Problems like these do assume a linear relationship between the variables. We're assuming that x and y are connected in a fairly straight line. As the number of miles increases, the time of your 10K decreases. These models do have only a limited range of usefulness, however, because not all data is connected in a linear relationship. Not all data follows this straight line relationship. The linear correlation of the data describes how closely the data points are clustered along the trend line. The correlation coefficient R, where R is greater than or equal to -1 and less than or equal to 1, numerically describes the degree to which the two variables are related. So the closer we are to a straight line, the more closely they are related. A positive correlation indicates that the two quantities increase or decrease together. As one goes up, the other goes up. As one goes down, the other goes down. A negative correlation indicates that one variable increases as the other decreases. Thinking about our miles and our time in the 10K, as the number of miles that you trained with increased, your time decreased. That is a negative correlation. The closer that R, the absolute value of R, is to 1, the stronger the correlation between the variables. If R equals 1 or R equals -1, then all the data points will be on a straight line with a positive or negative slope, respectively. So in this graph, for example, R equals 1. There is a point-for-point correlation. Here we have a negative slope, but R is still equal to -1. Here you can see the trend line is a positive slope, but not all the points are right on the line. Some are a little bit off. And this probably represents real-world data a little bit more than this. In reality, you're going to have some outliers here, some that are faster or slower, or whatever the data may be illustrating. So our R here is 0.7. Here in our negative slope, you can see that the points are scattered a little bit more, and our R here is -0.6. So the closer we get to 1, the closer we are to having a straight line. You can tell as our R got smaller that our points become a little bit more scattered. Outliers that I just mentioned, you're going to have some outliers. Outliers are points that do not seem to fit the trend of the scatter plot. Maybe you've got this positive slope, everything's kind of close together, and then you just got that one random dot out there hanging out. These are often ignored when mathematical models are constructed. However, there is a really great book I'm going to reference here called Outliers. Let's write it at the bottom. And it's written by a guy named Malcolm Gladwell, who's one of my favorite social psychologists, or sociologists, I guess is what you'll call him. He has a podcast called Revisionist History. He's written several books, but he talks about outliers. And he did a whole book where he studied these people who didn't fit with the trend line, who did something different from other people in their generation or people in their careers, and something about them made a significant difference to where they became really successful at whatever it is that they did, whether it was hockey players or computer experts like Bill Gates or fashion designers. He looked at these people who didn't fit the trend and were considered outliers and examined what about them helped them be successful. It's a really fascinating book, and while it doesn't really have a whole lot to do with math other than the name Outliers, I think it has a good tie into how data like this can help us make predictions, but we're people and we don't follow these trends exactly. We're all unique and we're different, and there are different things about us that help us to be successful or to maybe not follow the trend or not follow a pattern. So I definitely recommend that if you're looking for a nonfiction book to read, or if you're interested in people who are just different from the people around them, you check out Malcolm Gladwell's book, Outliers. Today we created scatterplots and linear models, and we evaluated linear models. If you guys have any questions, be sure to ask me next class.